So let's say we have the expression log base 2 of 3 times log base 3 of 4 times log base 4 of 5, and so on, until times log base 63 of 64. The argument, or the top part of the logarithm, in each term matches the base of the next logarithm. Well, except for the final term, which doesn't have a next term. So for example, in the first term, log base 2 of 3, the argument is 3, and this matches with the base of the next term, log base 3 of 4, which is also 3. The argument in the second term is 4, which matches the base in the next logarithm, which is also 4. This pattern continues on until the last term, log base 63 of 64. So most of these terms have an irrational value, and we don't know the exact value of the irrational terms. But the pattern in the product makes the entire expression as a whole simplify nicely when we apply the change of base rule. The change of base rule, when applied to common logarithms, or logarithms of base 10, is log base a of b equals log of b over log of a, which is what I will be applying to each term in the product. So if we apply the change of base rule on log base 2 of 3, it becomes log of 3 over log of 2, and if we do the same for the second term, log base 3 of 4 becomes log of 4 over log of 3. And if we do that for log base 4 of 5, it becomes log of 5 over log of 4, and so on. So this pattern continues for each term in the product until the last term, log base 63 of 64, which we can rewrite as log of 64 over log of 63. The log of 3 term in the numerator of the first term cancels out with the log of 3 term in the denominator of the second term, and the log of 4 in the numerator of the second term cancels out with the log of 4 term in the denominator of the third term, and so on. So the log of 5 in the numerator of the third term would cancel out with the log of 5 in the denominator of the next term. And this pattern continues for the entire product until the last term, where the log of 63 in the denominator of the final term would cancel out with the log of 63 in the numerator of the previous term. So all we're left with is a single log of 64 term in the numerator and a single log of 2 term in the denominator. So this entire expression just simplifies nicely to log of 64 divided by log of 2. We have this nice cancellation precisely because the argument of each logarithm in the original expression is always the same as the base of the next term, except for the final term. This leaves us with only 2 terms to work with. So we can rewrite log of 64 over log of 2 as log base 2 of 64 if we use the change of base rule in the other direction. And this is just equal to 6, since 2 to the power of 6 is equal to 64. So log base 2 of 64 is equal to 6. So we had this product with 62 terms, and most of these terms we didn't know the exact value of. But using a nice trick, we were able to find the exact value, not necessarily of each term, but of the entire product itself. So this just turns out to be the integer value of 6. I always thought that this was a nice problem.